Hi. Who of you has a 3D printer? Yeah, I was hoping so. Okay, and who of you that has a 3D printer is designing models themselves that they print? Oh, wow. Very nice, very nice. Okay, and do your designs work on the first try usually? Somewhat, okay. I'm going to start off here by making a very bold claim, and I will say that designing parts that just work first try is totally possible. Parts that always fit, that don't break, and that never fail to be printed. And now I guess you might be a bit skeptical, so why do I say this? Well, because 3D printing, like any other manufacturing process, it isn't magic. Whether a part works or doesn't work is subject to some fundamental rules. And if we understand these rules, then we can learn how to make robust designs that just work. And this discipline, that's called design engineering. We could call it the art of making or perfecting the shape of mechanical parts. I think a lot of you will agree that getting a 3D printer is an absolutely eye-opening moment. Suddenly, there is this whole new world of possibilities of what you can do. You can suddenly create complex physical parts to solve real problems around you that you maybe didn't even notice you have before. And you can do so for laughably cheap compared to other manufacturing methods. It's absolutely crazy. And really all you need for that is your imagination, right? Well, that's not quite true, right? There are some limits to the parts that we can make. Even though 3D printing is often advertised as this technology that allows you to produce arbitrary shapes, but I think most of you will know that this isn't quite true. So first of all, if we want our parts to be functional, for example, we can't make them arbitrarily thin. The material isn't infinitely stiff. There is a limit to the material strength where it will just break. And also the fused filament 3D printers that most of us are probably using, they aren't even completely free in the kinds of geometries they can print. There are some shapes that work very well and others that are really difficult to print. And as I started figuring this out, this fascinated me a lot. It sort of led me down a path of trying to learn everything about how you have to go about designing parts that are going to work perfectly every time. And really, the 3D printing community is an amazing place for that. There are so many people who are experimenting with different design tricks and techniques and figuring out what's working well, what's not working so well, and documenting that. And most of those resources are shared for free online. So I've been collecting all these tricks that I found in the community, and also I've been experimenting a lot myself to see what works and what doesn't. And I want to share that with all of you. Of course, I only have 30 minutes here. I won't be able to talk about everything in this short time frame, but I have published a long-form blog article about all the nitty-gritty details of design for 3D printing, and I'll get back to that later. For now, here in this talk, I want to give the most important part, in my eyes at least, and that's the general approach to designing parts for 3D printing so they work well. And that sort of comes with the right mindset that you need for design. And most importantly, this isn't specific to any CAD software or any specific tool. This is more the abstract approach that you have to follow in your head, and then you can translate that into whatever CAD software you prefer. So let's go back to that design engineering I mentioned. What is that? And to go deeper into that question, we first have to answer something else. What does it mean for a part to work or to be good? That isn't really a precise term. And this isn't actually that simple of a question. There are a lot of different angles to this. The most obvious thing is functionality. Like, for example, does it fit? Let's say we have some mounting holes that our part is supposed to attach to. If our part doesn't fit to those mounting holes, then it is quite useless. Or we have some other physical parts that we want to fit to our parts, and we must make sure that they match to each other. Every mechanical part, in fact, will have a lot of mechanical interfaces that we have to connect to. And so if our part doesn't fit those mechanical interfaces to other parts, then it's quite useless and it's not a good part. That's the first functional aspect. The second one is, does it break? So the part, of course, has to be strong enough to withstand all the forces that it is subjected to. And this is a more tricky question. Like, if a part doesn't fit, you'll see right away. You'll print it, it doesn't fit, you're angry, and you reprint. But whether a part will break, that's really difficult to answer, because a lot of failure modes only happen over time. For example, material fatigue. You won't notice at first, but then after quite some lifetime, the part will slowly fail. Or if you have many, some will start failing. It's a whole mess. And you can't really know in advance how strong parts will be. You can't really calculate the strength of 3D printed parts. And so these are the functional requirements. There's, of course, some others, like, for example, the cost. Maybe if you do this for business, you care about what each part costs. You care about the weight, maybe, or you care about the size for non-functional reasons. And so I think these are all pretty obvious requirements. But behind those, there is an even more important one in my eyes. And that is, can it be made? Because if it can't be made, then we don't have a part to fulfill all the other requirements. So this is just as important as all the other questions, is designing parts that can be made well. And really, this is a tricky question, because it's not yes or no. It's not we can make the part or we can't. Well, sometimes that's true, but often there is a range in there. So, for example, there might be parts that you have to post-process for them to work, or where only every second part you print will be successful and every other one you have to scrap. Or you will need some special or expensive equipment to make the part. Let's say a more high-end 3D printer. And obviously, it would be better if those weren't the case. If we were to design parts that can be made well and don't have these sort of special requirements. So this is where the design engineer comes into the picture. The design engineer's job is to find the optimal compromise between all these different questions or requirements. So figuring out the trade-offs of, should we make the part stronger or should we make it cheaper, for example? Because you can't go one way or the other. You have to make trade-offs in a lot of places. So, cool. How do you do that? Well, the problem really is that we have all these questions. Well, does it fit? Is it strong enough? And we sort of have to answer those. And we don't just have to answer those once, we have to answer those usually in a lot of places of the design. And we can't really answer them to the last detail, because we'd have to do a lot of maths. We'd have to probably simulate the parts to try and figure out whether it's really strong enough or whether it will really fit. And that's not a solution, because that will take an infinite amount of time, and obviously we do not have infinite time. So we can't just answer all the questions to the end. We have to use some less precise methods during the engineering design work. And the answer to that lies in heuristics. So rules of thumb that we use during the design process to figure out what we should do when we don't know for sure what to do. These sort of rules, they guide us by giving us a sane default of, well, we could do it this way or the other way, probably this way is better. We don't know for sure, but there is a high likelihood. So we don't have to go and do all the maths of checking whether it will really work, and we sort of hope for the best. And most of the time that works out well. And these heuristics, these rules of thumb, they exist in every engineering domain, of course. Just to paint the picture a bit more vividly, in general mechanical engineering, there is, for example, the rule that you should always guide forces on the most direct path through your part as possible. Or when you design your parts, you should make the tolerances that you allow on the part as large as possible. And these are general rules that when you follow them, they will probably lead to your parts working great. And these sort of rules, that's what people have been figuring out over time. These heuristics, they encode the knowledge that the engineers have gained over time. So, of course, this is what I've been looking for 3D printing. Design for 3D printing is really these rules, and I call them rules, but they're not really rules as in you have to follow them, as I mentioned. But I wanted to collect these rules specifically for designing parts for 3D printing. And now I will dive into some topics related to that. The first one being design for strength. That's the does it break question. It isn't actually that specific to 3D printing. Every part has to be designed to be strong enough. But 3D printed parts have some special properties that affect the part strength in non-obvious ways. So that's what I want to look at. The first being that 3D printed parts are made of layers. And these layers, they are stacked on top of each other, and that leads to different material properties in different directions. So you have the direction across the layers and along the layers. And the problem here is that the adhesion between the individual layers, it's not perfect. So when you pull the layers apart, which we would call tension, this tension resistance of the part will be less strong in the direction of pulling apart the individual layers compared to pulling on the along the layers, and so stretching the individual filaments that the printer has extruded. So we can generally say, and the exact numbers, they differ a lot between printers and setups, but generally parts will be more strong along the layers than across. So when you design your parts, you should design them such that you orient the tensile forces to be parallel to the print bed. So here is this example, that's a screw, and a screw is of course loaded in tension along the threads. And so what we can, so that's bad of course, because we now have the tensile strength in the weakest direction. So maybe it might be better to put it flat on the print bed. And then you have a part that is a bit better in terms of its strength. But really, there is another important thing here, and that's for the design process. When you design parts, one of the very first things you should do is you should decide on the print orientation. And you make this decision based on what I just mentioned, the tensile forces that your part will have to withstand, and you decide, okay, this direction is probably where most tensile forces will be, so I orient that flat against the print bed. So you decide on this orientation very early on, and then every further step in the design is based on top of that. So you have to make sure that you think through this decision quite carefully, because changing that later on is pretty difficult. It's like when you have when you choose a framework for your software project, choosing a different one at a later time is very difficult. And similarly, you should make sure to do careful consideration of the part orientation. And generally, this is very important. When you do your CAD work, the CAD software shows you a simplified model of reality. It shows you a perfect solid volume. But in your head, you should always imagine the structure of the print as it would be produced by the printer from that volume. And then when you change the volume's shape, you should think about how that affects the layer structure. But the layers aren't the only thing that's interesting about 3D prints. The other thing is that 3D prints are actually mostly hollow. You have this solid shell and then a mostly hollow infill. And let's say we have this part and it's not strong enough. We could just fill it with more material to make it more strong, right? And this does work. We get a stronger part, but it's actually really inefficient to do that because we're adding a lot of material that doesn't help strength in the general case. The reason for that is that most parts aren't actually loaded in pure tension or compression, like the screw, but actually most parts are loaded by bending forces. And bending forces have an interesting property. There is a neutral axis across the center of the part where the internal stress is 0. And then as you go outwards from this neutral axis, in one direction you get higher and higher tension forces, and in the other direction you get higher and higher compression stress. So actually, material does most to resist the bending forces when it's right at the surface. So really, the better choice in the general case is to make the shell thicker than to just fill the inside. Because in the middle, the infill won't do anything for strength against bending moments, because that's where the neutral axis is. So, okay, we can make the part stronger by making the shell thicker, right? That's one way, but there's another one that for us as the design engineer who cares most about the shape of the part is much more interesting. And that's, we can just move the surface to be further away from the bending, the neutral axis of the bending moment. So by doing that, we don't add that much more material, we just move the existing material of the surface to a place where it does even more to resist bending. In this case, this would mean changing the height of this beam to be more, like, let's say, increase it by a factor of 2, and then we get a much, much higher resistance against this bending force without adding more material. And I say without adding more material because really we're adding more volume, and the volume is empty space. So you always should think more about the surface area of your parts than the volume. Because the volume is mostly hollow, it doesn't do much for strength. So always think more about the surface. Okay, so the next thing is, does it fit? And in the engineering world, this is the tolerances. So how far can a part deviate from its shape for it to still work? So usually you'd go about this by defining functional tolerances. You would, for example, let's say we have these mounting holes somewhere, and we have a part that we want to mount to it. We add 2 holes to it, and then we can put some screws through there. Now, the tolerance on this dimension, or the limiting tolerance from a functional perspective, is how far can those holes move to the side for the part to still work. And at this point, if they were to move any further out, then we can't put the screws through anymore, so that's the limit. That's the tolerance limit we set. The problem here is that maybe our 3D printer isn't able to hold this tolerance limit. So what do we do? Well, you should think about it the other way around. You should consider what are the tolerances of the manufacturing process, so how accurate will the parts be that my 3D printer makes, and then use that to guide your design. So in this case, you might notice, okay, this tolerance limit for this configuration, that's too low. My printer can't do that. What you can do as a designer is you can make the holes bigger. And now the tolerance limit would move a bit more outward. And maybe your printer is then able to actually manufacture that. So let the manufacturing process, in this case the 3D printing process, define your tolerances and then choose your design accordingly, rather than going the other way around as the traditional method is. So now the natural question is, okay, so what are the tolerances that my 3D printer has, or that generally 3D printing has? Because usually we wouldn't want to design for a specific 3D printer. And I have to disappoint you, I can't give you numbers, because it depends a lot. It depends on the shapes that you're printing. So for example, here we have this box with square corners, and think about what the printer does when it prints those corners. It has to stop and then move in a completely different direction. So there's high acceleration. High acceleration means high forces on the frame of the 3D printer, which means it will shift slightly. You will have worse tolerance on those corners. You could fix that by making your 3D printer more stiff or by tuning the tolerance. But as a design engineer, you fix that by getting rid of those corners. Instead, if you add fillets, so rounded off corners, the printer now has to take much lower acceleration paths because the direction is changing gradually, and it will always print that with much higher accuracy. And even printers that aren't perfectly tuned against ringing, for example, they will be able to print that without much difficulty. And similarly, there's a lot of other things that printers can do better or worse, which I'll quickly skim over. For example, overhangs beyond a certain limit, or large flat surfaces where warping due to thermal stress becomes an issue. There's one more thing that I actually want to show, which is what do you do when the tolerances of the manufacturing process of your printer just don't cut it, when you need more. And there is an amazing little trick that you can use. If you can't make it precise, make it adjustable. So for dimensions where you need higher accuracy than what your 3D printer can give you, add adjustment mechanisms. That's not a silver bullet. You always add additional degrees of freedom that don't help. But these adjustment mechanisms allow you to get fine tolerances that you otherwise wouldn't be able to hit. So just some examples, you could use oblong holes for screws, or you could have two opposing screws that clamp apart and then you can adjust the position. You could oppose a screw. Come on. No? What's that? Let's see. Oh, that was a bit too far. Okay, here you could oppose a screw by a spring, or you could do what the industry always does, is shimming. So you see the small metal piece that's 0.2 millimeters in size. You just stick that between the two parts, and now you got your dimension perfectly on point. Okay, so that's tolerances. Now the question, can it be made? So let's assume it can be made, but we want to make it better. So that's why I called it process optimization. The first and most important thing here is support material. You can use support material to support structures that otherwise can't be printed. Like, for example, here, this screen structure supports this overhang. But really, those supports, they add a lot of headaches. You have to post-process the parts. Often you have to tweak the slicer to make them work perfectly. You have a rough surface where the support meets your part, which has bad tolerance if you care about that surface. So if you can, it's better to avoid them. And often you can, very simply. Like, for example, here we could just add a angled surface beneath this overhang, if the part interfaces allow that, and that makes it much more easy because now we don't have supports anymore. There's another nice trick. For example, you could flip a part to 45 degrees. Now you may have bad adhesion problems, so that's a trade-off to make, but now there is no more long bridges like it is here. And really, trade-offs is the name of the game. Support material, avoiding, and strength are often at odds. So here I have a part on the left. It doesn't need supports, but the direction is bad for strength because this little hook is across the layer lines. On the right, the strength is better, but now we need supports. So you always have to make those trade-offs. Of course, this was just a very, very small amount of information on the different areas of the strength of parts, the tolerances, and the process optimizations. And there is a lot more. Also, there's other areas, like, for example, you can, in 3D printing, functionally integrate many things into a single part, which in traditional manufacturing would be prohibitively expensive. You can use flexures to add mechanisms that can move, or you can do print-in-place designs. Also, you don't always have to do everything in 3D print. You can also combine 3D printing with other things, like the most common one would be machine elements like screws or other hardware like bearings. Or you could embed other materials into 3D printed parts. And so I hope I got a brief primer of this topic out now. And as I mentioned, I have this article where I went into much more detail on the things that I have found. And really, for me, this is just the beginning. This is the list that I have collected so far. And I would really love to chat about this topic more, because I think there is so much that we as a community can bring together by collecting these rules and by sharing them with each other. So please reach out, and if you are interested, here would be the link to the full article.
Thanks a lot for this really cool talk. So we have 10 minutes for questions. Are there questions? We have like several mics along the aisles. If you have questions, ask them here. Also, if you have questions from the stream, we monitor the IRC and Matrix channels, so we have a signal angel here for questions. But if we do have questions here, let's start here in the front.
Hi, yeah, thank you for this wonderful talk. I would be interested to learn more, like, what are your current fields of interest in 3D printing? Like, what are the things you yourself want to learn more about?
So my main use case for 3D printed parts is purely functional designs. Like, I had this teaser picture at the beginning, I think. This is, oh, come on. Yeah, don't use new technology when you do a presentation. Let's see. Come on, there we go. So integrating standard machine hardware, like in this case some pneumatic cylinders, with 3D printed parts to design automation systems for much cheaper than the industrial systems would cost. And there is a very interesting place here, because now we're replacing very stiff machine frames with the very compliant 3D printed parts. So you have to get quite creative to still achieve good repeatability and make sure that you work around the sort of limitations that 3D printing has. But it is actually surprisingly possible, and I can really just suggest to everyone who's interested in this sort of area, just give it a try. You can get quite far, you can get amazing accuracy, even though you're not using the high-end components that industrial systems are using.
Thank you. Another question, I think you were first at the mic number 4.
Yeah. Thanks for the talk. Which programs do you advise us to use?
Okay. So this talk was specifically not showing any specific CAD program. I myself use FreeCAD, and I'm a strong advocate, a very strong one. And actually, okay, let's see if I can live roll that. There is something I have for you, because if you do design for 3D printing, oh shit, I did not prepare to do this. I actually created a FreeCAD add-on that helps you do design for 3D printing. And I wish I could show you. It's called Fused Filament Design, and once I got it here, I will put it up on the screen. And this is, yeah, there we go. Look, does it work? Yeah, it's a FreeCAD add-on. It helps you automate common design for 3D printing shapes. Like, for example, here you can see certain examples. I will skip the details for now. Read the blog post. And that really makes you more productive. Maybe the same thing exists at some point for other CAD tools, but that's why you should use FreeCAD for your designs for 3D printing in particular.
Thank you. Next question, number 2.
Hi, thank you for the talk. Do you have any experiences with compliant mechanisms using FreeCAD, or do you have any tips if I'm interested?
So flexures, I would call it, so compliant mechanisms, they're a really tricky topic because the thermoplastic that we use, while on one hand it's quite easy to bend and it's compliant, so that's nice. On the other hand, it has some properties that are not so nice, so you can't control it as well as, for example, metal flexures. I do mention some things in the article, but if you're really interested, we could have a chat about it, because there is a lot of depth, and actually I did some yet to be published work on that as well, trying to integrate flexures into more complicated designs in the hopes of reducing external component count. But I have to say, it's really, really tricky to get right, to make them robust so they don't break over time.
Thank you. Where would we find you?
DECT 4016 or at the Rust assembly.
Thank you.
Thanks. Another question at number 4, I think, is the mic.
So the simulation is also FreeCAD, or where did you do this?
The picture of the simulation I showed, that was FreeCAD FAM. I actually don't use it much, but I used it to generate this one visualization, and it was surprisingly usable, actually.
Thanks for the talk.
Do we have more questions in the audience? I don't see anyone else at the mic or at the Signia Angel. I don't think so. Do we? No. Then I have another question. It's a bit of a Harold question because I'm not as deep in the topic as you. What is the most important thing for you about 3D printing? What makes you burn this much for the topic?
I think the main topic is that it allows us to share designs easily. It makes it that we have portability in physical objects, which just doesn't exist with traditional manufacturing, because either it's too expensive or people don't have access. And with 3D printing, we suddenly have the ability to copy each other's designs, to iterate on them in a way that we're used to from software, but doing the same for mechanical things. And I think there's huge potential there. I think we're not even close to using that to all its extent, and I would love to see it happening much more.
Thank you. We still have like 3 minutes for Q&A, and there's another question at mic number 1.
Hi, thank you. So the software is evolving, the slicers and also the 3D printers. So what has changed for you in the last couple of days or years? So like we don't need that much support anymore than we used to be. What changed for you, and what do you think will change in the next couple of years?
Oh, that's a good question. So I would say in general, the design rules that I'm working on here, they become less important over time because 3D printers get better, and as the general, let's say, population of 3D printers gets upgraded over time, you can have higher expectations. I try to always make my designs such that they target the common 3D printers that everyone has, so everyone can print them without problems. But these common 3D printers, they get better over time because people replace theirs with better ones. So over time, things are less important to care about. And well, at some point, maybe we'll get closer to, for example, what other additive manufacturing methods allow in terms of flexibility of design. But it's hard to tell how fast that will happen.
Do we have more questions in the audience? We still had a little bit time for more questions. Someone is standing up. Yes?
Hello. I got a question regarding the addition with other products, for instance, like glass fiber. Did you ever make experience with mixing materials?
I personally haven't so far, but I've talked to a lot of people who are experimenting with that, and I think it is a very interesting avenue to embed, for example, glass fibers or carbon fibers, not into the filament, but rather into the print, maybe during the print or afterwards.
Okay. Any more questions? We still have like 2 minutes if we want to run, but if there are no more questions, then I think a big round of applause again for Rahix and his great talk.